score. And sir has selected as the best TA, teaching assistant, during the PhD program also. And sir has now presently as a reviewer for many journals like IEEE Transaction on Industrial Electronics, IEEE Transactions on Circuits and Systems, IET Power Electronics, IEEE Transaction on Sustainable Energy, and Electric Power Components and Systems. Similarly, IEEE conferences also has a sir as a reviewer, and national conferences uh, for in the area of power systems and power electronics also. Sir has having the memberships, lifetime memberships of IEEE, IES, IAS, PES, and PELS. And sir has invited many lecture talks, industrial expert talks in various colleges like Assam Engineering College, Mizoram University, NIT Silchar, NIT Meghalaya, Manipur University, Bvrit, Narsapur earlier. So these are the many talks by the Dr. Debnath sir. So we welcome you, sir. So which a great personality with us for today's morning session. And now I request Dr. Deepnakar Debnath sir to take over the session and deliver the valuable information to our beloved participants. Thank you very much, sir.
Yeah, thank you very much. So yeah, as you've got an idea from this nice introduction, I mainly work in the area of power electronic converters and its various applications like electric vehicles, solar photovoltaics. So in today's talk, we are going to discuss about solar off-grid system. So for example, let's say if you have a home in rural area where electric grid is not available, how can you design a off-grid system or standalone system? So as you know, solar is a very good candidate for such areas. And since solar is not available all the time, you must have an energy storage element into the system. So we are considering battery for that. So which power electronic converter you select, how do you control them, what are the research challenges? So all those things I'll try to discuss in this 2 hours lecture. So since it's a long lecture, I'll try to go slow, and in between we'll try to take very short breaks, and maybe sometime I'll break and I'll ask 1 or 2 questions from your side so that it can be effort from both the sides, right? And I can promise that if you understand all the concept that I'm going to discuss today, you'll be able to take up some of them as your own research area also. And there are several open-end questions so which you can take care, and you can start writing your own research article also if you're interested. So with this, let me turn off the video to improve the bandwidth, and I'll start sharing the slides. And if time permits, I'll also show you some simulation on this concept that I'm discussing. Yeah, can you please confirm whether my slide is visible?
Yes, sir. Slides are visible.
Okay.
Yes.
Yeah. So though the title is a 2-stage solar photovoltaic based standalone scheme, basically I'll be giving a broad overview of what is a standalone scheme and how can you design it, how do you size, how do you control all those aspects. And on down the line, I'll be taking a few questions also, something that I have decided, something you can also ask to make it more interactive. And since this is the last lecture of this short-term course, I assume you already know how solar works and why solar is important. So I'm skipping all those. Maybe I'll be sharing you the slides so you can get all those data. It's not very, and how solar works, I believe most of you know. So I'm skipping that. If time permits, I'll come back and if you have any question, I'll discuss. But otherwise, I assume that solar, how it works, you must be knowing. So it's equivalent cell, everything. What I would like to start from is this one. So this solar for photovoltaic P versus V and I versus V. So IV curve and PV curves are generally known to almost everyone who starts working on solar photovoltaic area. So I'll start with this. How do we get this graph? If time permits, I'll come back if you have any questions. But otherwise, I'm assuming you already know these graphs. Claude. Now, generally, all of us starts with this point, and it is a first quadrant operation, meaning you have voltage and current. So you have voltage in this direction and current in this direction. So both voltage and current is positive. in this. So it is first quadrant operation. So this curve is very well known to us. But what happens if you extend those curves in this zone or in that zone? So basically you'll be operating in second or fourth quadrant. So this is how the complete IV curve looks like. So this is the first quadrant curve which we generally study. So this side your voltage is positive, current is positive. But if you go into this side, actually your voltage is negative, current is positive. That means your power is negative, which implies that instead of generating power, your solar cell is actually now consuming power or absorbing power. And if this amount of power absorption exceeds permissible limit, your solar cell may get destroyed. Same thing happens when you try to force negative current through the solar photovoltaic, right? This fourth quadrant. So voltage is positive, current is negative. As a result, instead of generating, the cell actually is dissipating power. And again, it is dangerous for the solar cell. After some time, your solar cell may get damaged. So we should be providing adequate protection in the system so that we never operate in quadrant 2 or quadrant 4. So how do we do that? Before that, let's try to understand this quadrant 1. So if you have simple example, let's say I have a solar photovoltaic cell which is having plus minus terminal as shown, and if you connect a battery to it with this polarity, plus matching with plus side, so this gives you first quadrant operation. So current, I'm assuming your battery voltage, let's say it is around 12 volt, and solar voltage range maybe 0 to let's say 24 volt. So this 24 being the VOC, and this point being the ISC point in this graph. So as soon as you connect a 12 volt battery, so right now if you assume this to be 24 volt, so your operating point will be at the mid of maybe somewhere here, 12 volt, and this will be your current. So current is positive, voltage is positive, you are in quadrant 1. Now if you connect the battery in reverse direction, so what you are basically doing, you are applying a negative voltage across the solar, so you are entering into second quadrant. So this you should not allow. So sometimes what happens is that by due to wrong connection of your power electronic converter or maybe a wrong control strategy, this situation may arise. Sometimes this situation may arise due to non-uniform operating conditions. Yes. So what to avoid this, what generally we do is that we connect a diode like this, so that as soon as your negative voltage tries to exceed the cut-in voltage of this diode gets turned on and your operating condition gets restricted somewhere here. So this voltage being the cut-in voltage of the diode, let's say it is around 1 volt. That is how power dissipation will be limited. And also we put a diode like this to prevent negative current going inside the solar photovoltaic. So you can avoid fourth quadrant. So these protections are very important. Whenever you are trying to do some testing at hardware level in your lab. Now let's try to understand from size perspective. So this is one of the very common questions that students ask when I try to deliver talk on solar photovoltaic. So the question is, if you want to build a solar system for 1 kilowatt rating, what is the area required? So to understand this, we need to understand a concept called standard test condition. So what it says, this condition is defined as if you have 1 square meter area, so 1 meter in this side, as you can see, 1 meter in this side. So this entire area is 1 square meter. So if you have 1 kilowatt of power falling in 1 square meter area and your ambient temperature is 25 degrees centigrade, so that condition is standard test condition. Why? And there is also another condition known as NOCT. So why these are important? Now let's say you want to compare performance by different manufacturers. So they manufacture solar panels at different voltage and currents. But if you want to compare which one you want to take, so you have to compare them with respect to a given test condition, so that you can compare which one is giving better output, which one is giving better efficiency. So this is one of the common test condition. So at 25 degrees centigrade, if solar power falling in 1 square meter area is 1 kilowatt, what should be the electrical power output of your solar panel? So you might be knowing that solar panels, which are commercially available, they have efficiency of the order of around 10 to 20%. Typically around 15%, you can assume 15 to 18%. So if 1 kilowatt of solar energy power is falling in the area, then you have the solar panels, right? So they will convert it to electricity. Since they have around this much of efficiency, let us try to assume that you have only 10% efficiency to make this calculation easier. So 1000 watt power is falling in this area. After conversion through your solar panel, it is becoming 100 watt because it is 10% efficient. So in other words, if you want to get 100 watt of power, electrical power, which is useful for us, you need an area of 1 square meter, right? This area. So to get 1 kilowatt power, you need 10 square meter area. That is kind of a rule of thumb, you can say. It's a generic statement. Of course, you can argue that if my efficiency is around 15%, then this area will come down. That is true, right? But you have to consider this overall system efficiency also. After solar photovoltaic, you will have a DC-DC converter or power electronic converter. Then finally, you will get load. So again, this overall efficiency will come down. And you generally don't get 1 kilowatt insolation every time, right? It is kind of a peak for us. So if you want to consider all those cases, this gives you a rough figure. 10% you can consider as a kind of a rough figure, and that's how you get this number. To get 1 kilowatt of solar useful electrical power, you need 10 square meter area. The next question is, how do I calculate how much power I need for my home? So let's say, as I told in the beginning, let's try to assume that we are designing a standalone scheme for rural area when grid is not available. So you have a home there. How do you calculate how much power you need? So to understand this, you have to understand what are the typical power rating of commonly used appliances. So in almost in all our home, we will be having one maybe ceiling fan, and then maybe we'll be having a TV. It could be LED TV, right? Then you'll be having several bulbs, LED bulbs, maybe LED tube light or LED small bulbs. So you see all those appliances which you want to use, and from their power rating, you can calculate how much power you need. So for just quick reference, I have given most of the commonly used appliances and their typical wattage figure. So it will be useful for you. So I believe in some or the other way. So let's try to take an example that you are designing a home and you have an 18 watt bulb, right? A lamp. And let's say you have 60 watt fan and you have 75 watt refrigerator. Let's say we have 3 loads that my home is having. And now we'll understand the difference between power and energy. So power into times basically gives you the energy. So first we'll take up this example. Let's say the bulb that I'm having in my home, that has to be that is supposed to give me light for 4 hours during the night time. And let's say the fan, I want it to run only during maybe the during the noon time. So let's say it is just for 2 hours. These are of course a rough figure for calculation. You can change all this data. And your refrigerator generally kept on for 24 hours, but there is a compressor which turns on, and there is again some time for turn off. Again it turns on. It is not continuously working. That's why you see some sound coming from your refrigerator. Sometimes your compressor is on, sometimes is off. So most of the compressor, they have 50% duty ratio. So they are active for some time, they are inactive for some time. So basically they cool down and they again wait till temperature rises above some value. So that's why this 0.5 factor is coming. So 24 hours they are on, but effectively they are on for 12 hours. So you know this power rating, you know the time for which an appliance is to be working, and that is how you get the energy demand. Okay, so finally you can calculate energy demand for your home, and from this you have to calculate what is your solar size required, so which will take up sometime later. We'll come back to this slide again and we'll see how can I size my solar system. Okay, so the next question is, now we understood what is my power rating. Now next question comes to implement the overall solar this off-grid or standalone scheme. What are the main component, major component required? So first we have to understand this is an autonomous system because grid is not connected. You have to design a self-sufficient system for your home, right? And we are considering solar as our renewable energy sources. And since solar is not available throughout the day, especially during the night, and you need a battery as a backup element. So I need a solar, I need battery, and of course we'll be talking about AC loads, and if time permits I'll also talk about DC loads. So AC load we know it requires 230 volt 50 hertz supply single phase. So to make interface between solar photovoltaic battery and load, you need power electronic converters, and to control them you need maybe a microcontroller or a DSP or FPGA. So you have some sensing arrangement, you keep on checking the load voltage, solar voltage, battery current, and all those information you feed it to your controller, maybe the processor, that it generates duty ratio for your power electronic devices. So this is how the overall scheme looks like. Now how do you decide which power electronic converter you are going to use? That we'll see shortly. So what are the key decisions that you have to make? First decision, for the solar photovoltaic, what should be the voltage and power rating? Similarly for the battery, of course you have to understand it should be bidirectional power flow. And again, what should be the battery voltage? What should be its rating in an ampere hour? And what is the load sizing? So load sizing we have already understood. It is my home, so I know what power I need, apparent power or active reactive. And how to select power electronic converter, we'll see shortly. Now, just to make an example, right, we are considering, let's say our power rating of the house is around 250 to 1000 VA. It's a AC load, so we are concerned about the apparent power. So active power, and then you take care of the power factor into account, you get this apparent power. So just to complete the discussion, so we'll be having solar photovoltaic and battery, and load is AC appliances, 230 volt 50 hertz. Power rating is around, let's say, just to make even easier, let's say our power rating is around 500 VA, so that we can take up an example. Yeah, so this we understood, solar curve also we understood. The next question is, what are the modes of operation that is important to decide which power electronic converter we are going to use? So this standalone scheme, in which modes you have to control them, what are the main control objectives that we need to understand slowly. So let's say your load demand at any point of time, let's say it is around 100 watt, right? And your solar has capability of giving you 200 watt. So you have 100 watt extra power, you would like to charge your battery, right? So if your battery is not fully charged, it can take that 100 watt of, we work in MPPT mode. So basically we keep on extracting maximum power from solar photovoltaic, and that extra power we charge the battery. Similarly, if we have some situation like solar power is 100 watt, but load demand is 200 watt. So then extra power should come from battery is 100 watt. So if battery is not fully discharged yet, battery can give 100 watt of power. So again, we can work at MPPT mode. What is MPPT mode? We are operating solar photovoltaic at this peak point. So MPPT algorithm we use and we control such that your system operates at MPPT. Now let's think about a situation. Your solar power can give you 200 watt. Your load demand is 100 watt. So you have 100 watt extra power. And let's say your battery is fully charged. So what do you do with this extra 100 watt power? Right? So this extra 100 watt power, no one is there to take. So what you do is deliberately you operate some other point. So if your MPPT point was 200 watt, we deliberately operate at some other point so that power output from solar is 100 watt, which is same as your load demand. Of course, we are neglecting losses in the system to make our discussion simple. Yeah, so I repeat, my solar has the capability of generating 200 watt, but since battery is fully charged and load demand is only 100 watt, so that extra power, there is no one to take up. So we are reducing solar output by operating at some point which is not MPP. So we are operating at some other non-MPPT point. Right. So as you understand, there is for same power level, there are two operating points here. One is on the left side of MPP, another one is on the right side of MPP. So most of the time we design our control system such that our operating point shifts to this point on the right side. So once we do that, we call it non-MPPT mode. Why non-MPPT? Because solar operating point is done at a non-MPPT point. We deactivate the MPPT algorithm. Then another case may appear when solar power, let's say it is very less and load demand is high, but battery is already discharged. So battery also cannot supply your load demand. So you have to shut down your system, or maybe you can serve only critical load for time being. That you can do. And there can be another mode when solar power is totally zero during the night time and battery is supplying the load demand. So this is actually a subset of this. So some control system need this, some can be clubbed with this MPPT algorithm. So this basic definition we need to understand. So we'll be talking about MPPT mode. So here I am assuming my battery is healthy. It can consume, it can supply whatever power it requires. Once battery is fully charged, we go into non-MPPT mode. When battery is fully discharged, you have to shut down the system, or you can actually take care of only critical load, or you can charge the battery with little bit of power if you have any from solar. So again, you can break these modes into some smaller modes and you can discuss. So to summarize, if you want to design such a system, what are the challenges, right? What are the research challenges that you have to handle? So first challenge is when you're designing a system for your home, you'd like your DC voltage to be lesser from safety perspective. That is one of the issue. Another issue is that if you are designing solar photovoltaic voltage high, that means you have to connect several solar panels in series to increase the voltage rating. The maximum commercial voltage available with different manufacturers are generally around 36 volt VMPP of a single module. So you have to connect several of them in series to increase the voltage rating. And as you know, problem with series connection is that they have to carry same amount of current. So if one of them is shaded, it will affect entire string of power output. So generally for home appliances, we try to reduce the voltage rating, and we, instead of connecting them in series, we connect them in parallel, because parallel connection is more is good as compared to series connection for shading kind of problems. And you know, in home environment, you must there are high chances of having shadows from nearby tree or some chimney, or you know, there are several sources. So we'd like to connect several of them in parallel, so that if one of them is also slightly shaded, it does not affect the other. So same thing is for battery. Thumb rule for battery is that if you have your power rating less than 500 VA, you go with 12 volt battery. 500 to 1000, you go with 24. Then you go with 48, maybe up to 5 kVA. And after that, you go with 96. So this is typically the rough figure. Because commercially available lead acid battery for home appliances, we generally go with lead acid battery because these are cheaper batteries, and they come with a 12 volt packing, right? So if you want to increase the battery voltage, you have to connect several of them in series, and then charge equalization problem comes. So to avoid that, you can of course do that with some precaution, but otherwise for very low power system, you can use 12 volt battery. Most of the commercial inverter from Microtech, Suchem, Luminous, all of them generally use 12 volt battery for home inverters. Now, as you can understand, so just for an example, we'll select 36 volt just to make the discussion complete for both solar and battery. And you can understand your load voltage requirement is 230 volt. So you have to give a high voltage boosting. So that is one of the challenge. Another is you have to ensure maximum power point tracking. You have to protect your battery from overcharge and over discharge. And you have to control your load voltage at 230 volt, and you have to ensure this is sinusoidal. So you have to control your converter properly. So you see there are several research challenges, several challenges rather to satisfy, and that is why. And of course, on top of that, you have to ensure that overall system cost is minimized, efficiency is good, size should be less, all those other issues. But these are the technical challenges. So let's see how can we solve these challenges and can design a system. Okay, so first option is that I connect my solar photovoltaic directly to the load, which is not possible. It's very straightforward because it is a DC, it is an AC. So this is not possible. Second is, what about I have solar photovoltaic, which is DC, load is AC. So connect an DC to AC converter, right? So this is also not a good solution because the degree of freedom in its control is only one. So either you can control input voltage or output voltage, right? You cannot control both of them together, which means either you can achieve MPP or load voltage control. Both of them you cannot control together, right? Because you have only one control parameter mainly. So to solve this, one of the second level solution could be, I have a DC-DC converter and I have for doing MPPT, and I have DC to AC converter for controlling the load voltage. So this is one of the very important Viva question. So if you have this kind of system, so solar giving you DC, then you have a DC-DC converter and followed by a DC to AC converter, and you have single phase load. So either this scheme is suitable. So most of the student will think, yeah, this is possible because DC-DC converter is doing MPPT, DC to AC converter is doing load voltage control. So it looks pretty good. But the main problem which they overlook is the term power balance. Right? What is power balance? See, if whatever power is being generated by solar, it has to go somewhere. Since there is no energy storage element involved in the system, the load has to take care of the same power. So that means P load has to be equal to PPV, right? Now, for a given time, your load may be something, right? Maybe your load demand is 100 watt, but your solar power may be varying. It can be 100, it can be 200, it can be 300. So you can see a clear imbalance in the power during some time, right? Because temperature and irradiance will be varying. So your solar power is varying. So how can you make sure that your load demand is also varying? Load demand is not in your hand, right? So this system cannot work. So what will happen is that if you keep on doing MPPT, we connect a capacitor in between generally, right? So this extra power, let's say if you have extra power 300 watt and load demand is 100 watt, So if you keep on doing MPPT, so solar will keep on giving you 300 watt. This load is taking 100 watt. So that extra 200 watt will now come into your capacitor. In your capacitor, the voltage will keep on building up, and after some time you will see a boom, right? Your capacitor may blast, and it will be smoke all around. Maybe it will be risky for you also. So that is why this scheme should not be used. So what is the solution? You have an energy storage element to take care of that balance amount of power. Yeah. So after this slide, I'll take a small break and I'll ask you if you have any questions. Otherwise, if I'm talking continuously, it'll feel bored. So I'll take up this question and then I'll stop for 2 minutes to see if you have any questions. So if you have any question, please maybe you can type in or you can prepare which question you want to ask. So this is one of the very important question again. It's a Viva question as well as is very interesting question to understand. So let's say I have a solar photovoltaic panel. I'm showing it by this, and I have a DC load, and I have a buck converter in between. How a buck converter looks like? DC-DC step down converter. Okay. This is C. This is R. This is L. This is a diode. This is a switch, and I've connected it like this without any capacitor. But in most of the commercial inverter or whatever research article you'll see there is a capacitor actually connected here. So why this capacitor is connected, why it is required, we'll try to understand. So first, let's assume that this capacitor is not there. So how this current will look like? Right? So when switch is on, current will be something. When switch is off, current will go down to 0, right? So S on, S off. So when switch is off, PV current has to go to 0, right? So when PV current is 0, that means you are operating in this zone. You see PV IV curve, current is 0 here, right? Current is 0 on this line, voltage is 0 on this line. So this point, and on where we want to operate, we want to operate at this point, VMPP, right? To extract maximum power from solar photovoltaic. So we cannot have the luxury of making PV current 0, because then we'll be operating sometime here. So if your duty ratio is around 50%, so half of the time you can see you're operating at VOC because current is 0. So that is not MPP, right? We want to operate at MPP. So that is one of the reasons that we connect a capacitor here. So when switch is off, the PV current can charge the capacitor, and when switch is on, both PV and capacitor can discharge the current. So this capacitor will help you to achieve better maximum power point tracking performance. And of course, it will help you some EMI, EMSU issues. So let's not go into the detail. So a similar problem comes in your grid connected inverter or single phase inverter. Let's say you have a solar photovoltaic, you have an inverter, DC to AC, then you will be using a filter to filter out all the harmonics. And finally, if you want 230 volt or something, maybe this can be PV in between, there may be some other DC-DC converter. So how do you decide this inductor value? How do you decide this C value? How do you decide which switch you want to use? What should be their rating, right? So all those are very interesting thing to learn. Of course, in today's lecture, it is not possible to cover. If you are interested, you can drop me a mail or maybe we can discuss some other time. How do you decide this should be how much millihenry? What should be the rating of this capacitor? How do you decide? What is the current rating of the devices? All those things we can discuss. How do you select this capacitor for grid connected inverter? How to select? So all those things we can maybe we can discuss some other day, not today. These are very interesting thing. How do you size these elements? So with this, I'll stop. And if you have any question, please let me know. I can quickly take up maybe a few questions.
Sir, in this slide, the example you have given,
Yes.
that PV cell connecting with a buck converter. If I connect a boost converter, whether the same problem will happen?
Yeah, that's a very, very interesting question. No, then at least your same problem is not going to happen because you have a inductor there, right? So let me draw this. Yeah, this is an inductor and this is a boost converter, right? So this now you have to understand how this current waveform looks like for a boost converter. So current waveform could be something like this, right? When switch is on, current will be increasing. Switch off, current is decreasing. So your operating point, let's say this is the average operating current. Let's say this is 10 ampere, and this peak, let's say it is 12 ampere, just for understanding, and this is 8 ampere. And let's say this 10 ampere is your IMPP because you want to operate at maximum power point. This is 10 ampere. So what you can see is that actually your operating zone shifts between this zone. So this is exactly 10. This could be your 8. This could be 12 amp, right? So you are not exactly operating at MPP. Now you will be shifting between this zone. So that is why your 100% MPPT tracking efficiency is not achieved. To solve this, what you can do is you can increase your switching frequency. Switching frequency you increase, so your ripple will come down. You can increase your inductor value so that this ripple will come down. Or you can put a small capacitor here also. Yeah, I hope it's clear to you.
Yes, sir. Yes, sir.
Any other questions? Can anyone of you please check the chat box? I'm not checking that. If there is any question in the chat box, yeah.
Yes, sir. One student posted that is
Sir, one more
manufacturing
thing
of
I want.
PV cells also affect the efficiency.
I had two questions parallelly. Can one of you please? Yeah. Dr. Sharvanan, you go ahead. Then I'll take up.
Yes, sir.
Oh, yeah.
I think it's Mr. Tarun. They posted the question in chat box. Is manufacturing of PV cells also affect the efficiency?
Yes, very much. So how you are connecting all those PN type materials, right? Ultimately, inside your solar module, you have to connect all those cells together. So how you are forming that network, which material you are using to collect the current, all those things really matters. It's a very big deciding factor. Yes.
Another one, it's having J Nisanthi. One participants posted that, sir, what are the main objectives for charging EV by off grid?
EV by off grid.
Yes.
There is.
Yes, madam, your voice is somewhat disturbed. It's not clear. Mr. Dharana.
Hello.
Yes.
Yeah.
So regarding to PV modules, I would like to ask something. So when we are considering about the efficiency, materials are also affected by the oxidation process. So resistance vary in the solar cells, due to which efficiency reduces.
Yes.
So how much percent this is correct?
There, of course, there is a effect of variation of resistance depends on several factors. I can't tell you which factor affects by what percent. That I don't have. Maybe you can read some book on manufacturing of solar panels. Maybe I can suggest you some book, but I really don't have the exact figure.
So defects occur in the panels, which also affects the efficiency of the solar modules. Overall efficiency of the solar modules. So how can we overcome those effects to enhance the efficiency of the solar modules?
So you figure out what are the causes of defects. For example, you don't generally use your semiconductor material like this. You put a overall on the outer layer of them. You put a thin layer of glass material to protect them from external damages, right? And you take adequate measure. As I told in the beginning, that you have to connect a bypass diode and a blocking diode to make sure that your cell does not dissipate power, right? So you have to understand what are the various. Sometimes there is a fault due to your lightning arrestor, right? You're keeping it in a field. So you have to detect what are the various faults. There are so many faults, and for each of the fault, how do you take care. So you have to put a lightning arrestor, you have to make proper grounding of your system. So there are various ways to handle them.
Sir, I'm having my research work on the performance of the SPV modules, and I have considered many parameters upon this, which is affecting the efficiency. One is the partial shading, another is the oxidation process, which affects the metallization of the or metallization of fingers or solar cells. And I have also observed the resistance enhancing across solar cells of the modules. So,
you also consider what is the leakage current, what is the effect of parasitic capacitance.
okay.
They sometimes are one of the biggest reason for getting fire in your system.
Okay, okay.
That you consider. Then deposition of birds, you know, or some dust material, how they impact.
Yeah.
Effect of aging.
So main work is based on my effect on aging also. The
Yeah,
overall
so there are so many parameters, you know.
view of it. So
It's a
fair.
good work.
Okay, thank you, sir.
Welcome. Yeah, I thought one more question was there from the same participant who has this boost converter question.
Sir, am I audible? Hello.
Yes. Please go ahead.
Sir, one thing I want to ask, if I have a battery, the previous example you have telling us that there is a standalone system. So there will be a PV cell, battery, and the load. It may be a AC load. It may consider you as a DC load also. Suppose at the night, if I all the power is providing from the battery, then if I need to boost the battery voltage to a certain level to provide the enough amount of voltage to the load, then how do I know the battery capacity? Or how long, because milliampere hour rating will be the battery capacity. How long, if I boosting the voltage, then the battery, how long will sustain? How do I calculate that? Because I don't have the same potentials of the battery in my load side.
No, see, battery capacity are measured with respect to battery, right? So you'll be putting a battery. I'll try to address you. So you have a battery. To first, your aim should be measure the SOC and SOH of batteries. So basically, state of charge and state of health. So you're going to measure the battery voltage, battery current. Then what you are saying, you'll be having a high gain DC-DC converter, maybe, right?
Yes.
To give you load. So see, this converter that you are designing, you know this rough efficiency figure, right? Maybe it could be 95%, 90%, but that does not affect your battery SOC level. So what your SOC will entirely depend on your battery, whatever battery parameter you are sensing. From there you can determine. Then if you want to be more accurate, you just include the efficiency figure of your DC-DC converter that you are using. And then from that, but even if you neglect this, because most of the power electronic converter, they give you at least 90% efficiency. So you keep a factor of that, and then you know how much energy you're left.
Then that means how am I boosting that? That will not be affected.
No, you see, battery does not know whether you are boosting the. And there is one more, yeah, I forgot to mention this. So, for example, if you take about lead acid battery, right? It is, let's say it is a 12 volt, 100 ampere lead acid battery, right? Now, how do you define this? Sorry, 100 ampere hour. How do you define this 100 ampere hour term? So people will try to understand that.
For 1 hour.
No, I think that is a wrong definition. There's a catch there actually for lead acid battery. I'm not talking about other battery, please note, because lead acid battery we are using. See, this is generally defined on a 20-hour basis. So that means if you have 5 ampere current taking from battery, this battery can give you for 20 hours. Now, most of the people think if I have 10 ampere of current, it will sustain for 10 hours, right? And if I take 1 ampere of current, it will sustain for 100 hours. So this data is wrong. In most of the standard definition, this is the actually definition based on 20 hours. So if you are charging your battery with higher current than this, Like this case, instead of 10 hour, you may end up with 9.5 hour. So higher the discharging current, your effective capacity comes down. On other hand, if you are taking less amount of current from the battery, your effective capacity actually will go up. You may see around 105 ampere or maybe. That is the true definition of lead acid battery capacity. Am I clear on this?
Yes, sir. Now I understand.
Yeah. So you go, what is the exact definition of this ampere hour? You'll understand this point more. But I believe I gave you the correct idea. I mean, you understood the point.
Yes, sir. Yes.
All right. Yeah, so maybe let me again get started, and after 30 minutes or so, I'll take a few more interesting questions. Thank you for coming up with the question. And this makes the interaction more lively.
Then what about the tubular battery, sir? How to measure that AH load?
See, for any battery, what you do is you keep on measuring the voltage and current, right? And there are several ways to do this SOC. You have some coulometric process. Then based on Kalman filter, there are several SOC estimation techniques.
So can you say any simple formula to calculate the SOC of a battery?
Yeah, the basic standard is what you do is first you measure the VOC. So VOC will give you the initial SOC. Then plus you keep on integrating your current. Right? So what is charge? Charge is I into T, right? So if you keep on integrating your current, because current is not going to be constant in your system, right? Depending on load variation, etc. So if you keep on integrating your current, so if you are taking positive current, your charge will come down. If you're taking negative current, your charge will increase. So you keep on integrating your current and you add it with initial SOC, which you can get from the VOC measurement. That is how you can get the SOC at any point of time. That is a simple way of understanding. So you sense the current using some current sensor along with direction, whether it is positive or negative, and you have some integration involved in your microcontroller or DSP. So this is the ongoing SOC, and add with initial SOC, that gives you the basic SOC.
Okay.
Yeah.
Thank you.
Of course, this is a very basic process, you know. Most of the low-cost commercial inverter, they just measure battery terminal voltage, which is not very accurate, but still it gives you closer to the SOC. Just to give you an example, if you know a 12-volt lead acid battery, when it is fully charged, it will be around 14 volt. And when it's fully discharged, it could be around 10.5 or 11 volt. So, you know, if you measure this voltage, you know roughly what is your SOC. Yeah, maybe I request all the participants to turn off their mic and let me continue for another few minutes. Very interesting points are coming up. And then I'll again take up some of your questions. Okay, so this point we understood, importance of power balance, right? So if solar is giving you more power than load demand, there is no additional energy storage element. So this extra power will keep on charging your capacitor, and that capacitor voltage will keep on increasing. And after some time, your capacitor may get damaged. So this is the simple concept. So to understand this point, again, let's quickly revise this. If you have a capacitor at any point of time, let's assume that its voltage is 100 volt, just arbitrarily at any point of time. And at that point, P in and P out are the input power and output power. So there could be three cases. P in same as P out, P in greater than P out, P in less than P out. So what will happen to your capacitor voltage? So ideally, if input power and output power is same, your capacitor voltage is going to remain 100 volt, right? Same power is coming, same power you are taking out. If P in is greater than P out, the example we took, let's say you're taking out 100 watt, but you're actually feeding in 200 watt. So this extra power, so capacitor voltage will become more than 100 and it will keep on increasing. Continuously it will keep on increasing and then it will simply get damaged. And on the reverse side, if your power, you are taking 100 watt, but input you are giving 50 watt, So stored energy in the capacitor will try to take care of that additional power demand, and as a result, you know, your capacitor voltage will be falling. So it will become less than 100, and maybe sometime it will keep on reducing. So what is the conclusion? Observation: if you measure capacitor voltage, you know power balance in the system. So if you keep seeing that capacitor voltage is falling down, you know this condition. If you see capacitor voltage is constant, you know this condition, right? So this capacitor voltage measurement gives you energy balance or power balance in your system, right? So this is very important observation based on which our next control strategies will be developed. So of course we understood to take care of this balanced power, we need a battery in the system. So battery you can put just parallel to the solar photovoltaics, but you know MPPT will be hampered, right? Because battery voltage is quite stiff, but your MPP voltage may be varying. You can put your battery in between. So PV DC-DC converter, battery, then DC-DC converter. So this some low-cost solution uses this approach, but you know battery is connected in cascade, so it will be subjected to more stress, right? All the ripples the battery has to handle between these two converters. So to be slightly on the safer side, you can put battery through another DC-DC converter, a dedicated converter for controlling the battery, right? So you know it's not directly subjected to the additional stresses. So this could be easy and safe solution. So we'll go ahead with this. Before that, let's try to understand this problem. So this strategy we understood: DC-DC converter for MPPT, DC to AC converter for load voltage control, and a bidirectional converter for battery, because you need to charge and discharge the battery. So you have to control both the direction. For load, we need 230 volt supply, right? If your solar photovoltaic is 36 volt, you know, we take up this example. What could be this voltage? So let's try to understand from load point of view. If I 30 volt at the load, what should be this voltage, right? Because load should be our priority. So load demands 230 volt. What is the minimum required VDC? That depends on what inverter you are using, right? What DC-DC converter you are using. So in most of our study, we use single phase half bridge, single phase full bridge inverter, which is should be very commonly known to you. You know, there are 4 switches, and you use sinusoidal pulse width modulation, SPWM, and unipolar is mostly used, not bipolar. You take a triangle carrier, you have 2 modulating signal, you compare them, and that's how you get the switching pulses for all those switches. Again, what is the difference between unipolar, bipolar, how to control? This is a separate lecture itself, so I'm not going into that. The main important point is that after doing this sinusoidal pulse width modulation, this is the voltage gain expression. Again, how does this expression came? All those things, it's very interesting to learn, but let's not discuss today. So if you understand this gain expression for this inverter, you know, DC-DC converter, people know gain. Buck converter, they'll simply say D times input voltage. Boost converter, buck boost, everyone this, they very confidently tell. But for inverter, they don't know what is the, most of them, they don't know what is the gain expression. So for fundamental component of the output voltage, the gain expression is this. Vs is the input source voltage. Omega is the frequency 2 pi f of this modulating signal. And MA is ratio of V control by V triangle peak. So you're taking a triangle carrier, peak of the triangle carrier, let's say it is 1 right now here. So this will be 1 for this example. And V control is this modulating signal. So peak of that modulating signal, this value, V control peak. So this ratio is modulation index. So generally we keep triangle carrier fixed. We vary the modulating signal so that you vary modulation index, right? What is the range of MA? It is between 0 to 1 for linear modulation, right? We generally don't go into over modulation. So if you just do simple calculation, you'll understand to get 230 volt at the output using this kind of inverter, and you need Vs minimum is 325, which is basically peak of the supply voltage. But in real practice, what we do, we keep this around 360 to 400 minimum DC voltage required. Why? Because at the output you need some filtering element, then your load will see. So some drop will be there, some drop will be there in the switches. All these gain expressions are based on lossless scenario, lossless condition. So if you want to consider voltage drop in the filter inductor, in the switching devices, in the connecting wires, etc., then you keep some margin, right? You don't, this is the minimum required in ideal case. So you keep some margin, and that's how you should select 360 around or 400 volt at the DC voltage required. So this is 230 volt. Again, my load requires that. If you are using full bridge inverter, as we have discussed just now, BRI, you need around 360 to 400. Your battery voltage is, we are taking around 36, let's say. So now a lot of student has an understanding that they can use a boost converter here. DC simple boost converter they can use to have 36 to 360 volt. So it's a gain requirement of 10. Right? So theoretically this is perfect, but practical boost converter, if you design in your lab, you will see that the gain curve of boost converter, this is the duty ratio. Duty ratio will vary from 0 to 1. So boost converter gain starts from 1, right? And ideally it could be maybe go to infinite, but practically it looks like this. So this is gain of boost converter. So after you'll see, after a duty ratio of around 0.67 or 0.7, the gain, instead of increasing, it actually falls down. And at duty ratio exactly 1, your gain becomes 0. So practically, the practical achievable gain without sacrificing efficiency, and here in this efficiency will also be very, very poor. So considering all this practical aspect, the maximum gain that which boost converters are designed are generally in the range of 2.5 to 3, not more than that. Theoretically, it is possible to get infinite gain, but practically maximum gain with which you can design a boost converter is generally around 2.5 to 3. So a boost converter cannot be used there. Yeah, so one of the solution, let me quickly go through it. One of the solution is that you put a transformer here, right? So that your voltage gain requirement comes down, so that you can use simple boost converter there. So with this, yeah. So one example is you use a proper transformer here, right? Low frequency transformer to take care of the voltage boosting. So if you're using 36 volt, your DC bus voltage can be 72 volt. So using 72 volt, and as I told, I already gave V output fundamental is MA into VDC into sine omega t. Gain you apply. MA maximum could be 1, right? So you put 1 just for simplicity. VDC 72, right? So what is the RMS value of output voltage, and then based on that you decide what should be the trans ratio of your transformer. Right, so how does this scheme looks like in through circuit diagram? It looks like this. This is a simple boost converter, as you can see, just a boost converter. This is also a boost converter, as you can see. Now instead of using a switch, you are connecting another, instead of just a diode, you are connecting a switch which is bidirectional, so that you can have bidirectional power flow. So sometimes you call it maybe class C chopper in some of the books. So basically it looks like this. So this is your battery, then maybe there is a capacitor. So you can have current flow like this. When switch is on, current is flowing like this. Switch is off, this current goes like this. So this is one direction of power flow, and another could be when you turn on this switch, so current flows like this, and when you turn off this switch, current circulates like this. So this way you can control power in both the direction. Of course, this V battery must be lesser than this VDC, because from this side to this side is a boost action, and this side to this side is a buck action. So it's a combination of buck and boost converter basically. So this is that bidirectional converter. And here you can see it's the same single phase inverter, right? And at the output you are connecting a transformer so that you can get your desired load voltage. So this is how one of the simple traditional scheme looks like. And what is the problem with low frequency transformer? All of you will be saying, yeah, its size is more, right? Weight will be more, efficiency will be less, right? Typically, this is a problem with transformer. It's a bulky transformer. So of course you can design a high frequency transformer embedded into your DC-DC converter. So in one of the solution, we'll see that, how to do that. Okay, so let me get back to those questions again quickly, and then maybe let's see. So you remember we did an example. We took 3 load in our home and we understood what is my energy requirement. Now we are going to see what is the solar power requirement. And after that, we will again come back to this control philosophy. So this is what your solar power requirement is, energy requirement. Remember, this is energy. Okay. Now, all of you might be knowing that the solar irradiance over a day is not constant, right? It varies something like this maybe. Irradiance. During noon time, it will be peak, right? Maybe around 12 o'clock or so it will be peak. Right. So let us say at this point, if someday we are getting 1000 watt per meter square irradiance, so definitely during this time it will be maybe 200, there may be around 600, right? So if I am using a panel which can give me 1000 watt per meter square, that power is not available throughout the day, right? So if you want to simplify the calculation, if I had some figure which tells me, right, so during, let's say we start with 9 AM and solar power is available to, let's say, till 3 PM. But during this time, your solar power is not constantly available, right? It is changing. Sometimes it is at peak, sometimes it is at low, right? So this 3 PM to 9 AM, it is actually 6 hours. Just for an example, right? But during 6 hours, I don't get peak power available. So if I want to calculate for what duration I get this peak power, definitely it will be less than 6 hours. So that could be around, let's say, maybe for 3 hours. So that is basically average of this maybe, right? So you integrate this curve over a day, and that's how you get what is the total energy. And if you just want to have a feel like this power is available for what duration effectively, so that will be definitely less than 6 hours, right? So how do I know this? We know this from this map. This map tells you at various part of India what is the solar irradiance level, and for what duration you get that kind of 1 kilowatt hour the irradiance. So if you are in a place, for example, I am near Kolkata, so I see this color map, it will be somewhere here. So for me this factor could be 4, right? If you are sitting at somewhere here, you see your color map maybe somewhere there, so you know these figures, right? So that figure is this figure. So this is my energy requirement in entire day, and this figure giving me some kind of, so this is energy, right? This is power into time. So this is equivalent to the time information from which I'm getting 1000 watt kind of power. So if I, so basically if I divide by this number, I'm having this. So what is the significance? So remember, solar panels are rated in terms of watt, right? So for example, if you have if you have this solar panel with you, 110 watt, the P indicates peak. So this solar panel will say at maximum power point, it can give you around 110 watt peak power, right? But this 110 watt peak power, it can give you maybe during only the noon time, during peak sun hour, right? So if you are using 110 watt and you have solar power available for 6 hours, as we are discussing, so then actually you will think that I may get 110 into 6 energy, right? Watt into time. But that is not the case. This 6 is not, throughout the 6 hour, you are not going to get 110 watt. Maybe you are going to get 110 watt for some 3.4 hours. That is this number. And how, from where you get this? You get that from that map, right? So this power you are actually getting maybe for just 3.4 hours on an average basis. So that is how you get this. What should be the power rating of your solar panel? If you need energy of 1419, you don't need solar panel rating of this, right? Because this is the energy. You have to differentiate between the energy and power. So, you know, this is your solar power requirement, because throughout the day for some hours you'll be getting that power and you get the energy. So if you have, we are in example, what we have taken, that solar power module rating is 110 watt for us. So I need total 400 watt kind of power. I have 110 watt module, so I need around 4 modules. 4 modules each of 110 watt. So this gives me 440 watt. 440 watt peak power, right? And this in an overall day, I may get this power for roughly for 3.4 hours. So that gives me this energy. Remember, this is not a 6 hours, 9 to 6 or 4 p.m. whatever. It's not the case. It's kind of this ratio you have to take from the map. Okay, so this is done. Next question is, how do you do the inverter sizing? So solar sizing we have understood a little bit. If you have any doubt, again I'll come back after the thing, and quickly let me talk about this inverter sizing, how we are going to do this. So inverter sizing is to be done for power rating, right? Nothing energy storage is involved. At any point of time, it has to deliver power to the load. So it has to be done from power rating point of view. So whatever equipment you have, you see what is their power rating. It's not energy, power rating. So you add them together, right? This is the power rating, and you have to, and that is how. This is the actual requirement. Of course, you'll be selecting slightly bigger size than your requirement, right? It's a safety margin, and then maybe your inverter can be 190 watt or slightly greater. Sometimes you would take safety factor of 2, so it will be around 300 watt. Next question, how do we do battery sizing? That is very important. So for each day, we know what is my energy demand, right? You remember, we take 3 loads, for how long they have to supply all those things. This is your energy demand. And to complete the discussion, you take battery voltage 12 days and days of autonomy you select. So let's say during monsoon time, your solar is not available. So how many days your battery are supposed to give you power continuously? That is your days of autonomy. Without solar, how many days your battery can cater your load? So let's say it is 3 days. Okay, so how do I do battery sizing? Using this formula. So I know this is my energy requirement per day. I multiply with 3. What is 3? 3 is autonomy. Then I divide it by battery voltage. So this is energy, right? Total energy. So watt into time, watt hour. Then battery voltage. This watt hour is voltage into current, right? So VAH by battery voltage, that gives you ampere hour rating. All right. But there are 2 other factors I have considered, as you can see. What are they? These are very important factors. What is 0.6? 0.6 is kind of depth of discharge. So if you have a 100 ampere hour battery, right, you may assume that it will give me 100 ampere hour throughout. But you know, for lead acid battery, depth of discharge could be around 20 to maybe sometime this SOC from 100%, if you start reducing, maybe as soon as it reaches around 40% or so, we generally don't drain it further to increase life of battery, right? So why? For lithium ion battery, you can go up to 20% maybe for lithium ion. For lead acid battery, typically 40 to 30% below that we generally don't go, because there are a lot of problem comes in, sulfating, deposition of some materials that degrades your battery life. So even though you have a 100 ampere hour battery, you don't have the luxury to utilize all of its stored energy. So hardly you will be utilizing it for maybe 60%, right? So you cannot again drain out completely. So you have to put a limit somewhere. So that means effectively you have to oversize your battery if you want to ensure your battery life. So this 0.6 is for depth of discharge. Basically, you're oversizing the battery so that you don't need to drain out the battery entirely. And what is 0.85? That you can understand. See, when you have battery storage, as someone was already asking, battery to load, there is at least 2 inverter or converter coming in, right? So they will be having some efficiency, maybe 95% or 85% in total. So whatever capacity your battery has, it is not going entirely to the load. Some part is lost here, right? Lost in losses. So this factor is taken for that. So again, you have to oversize your battery. If you want to get 100, you have to make it maybe 110 or 115, right? So this is how you design your battery capacity. Yeah, last part is how do I do the solar charge controller sizing? So for solar, you know what is the maximum power, you know, maximum voltage, you know, because we have already selected the panels. So maximum power rating, I know, maximum voltage, maximum current rating, I know. So, and then you keep some safety figure, and that is how you're done. Yeah, it is already 11:20. So I'll quickly tell you the basic control philosophy.
Sorry for the disturbance. If you want to take 5 minutes break for tea something.
Yes, I mean I'm open to questions. That will be great.
Okay.
Yeah, I think I can stop here. Maybe if they have any question on the sizing, I can take up. Or some other control philosophies.
Hello, sir.
Yeah, please.
Can you hear me?
Yes.
Actually, I was asking that you calculated the solar panel specification for 110 kilowatt, 110 watt. My question is it available for any wattage? Like
yeah. You can get it for 275 watt, but typically not more than 300 as per my search.
300 watt or 300 kilowatt? You mean?
No, for single module. You know that terminology, right? From cell you have module, right? So single module you don't get more than 300 watt as per my search.
Okay.
You can start from as low as 10 watt, 5 watt, and you can go up to 275, 300, that kind of. It's a very variety of option available.
Okay. So out of that number of PV panels, can we calculate how many will be connected in series or parallel?
Yes. So that depends on your battery voltage, PV voltage level that you want. Once power rating is fixed, next question is whether you want to connect the number of modules in series or parallel.
Okay.
It's an iterative process, right?
Yeah.
Any more questions? So maybe in the meantime, just to have a different thing, I mean, I'm not discussing anything. I can show you some in MATLAB how you can implement all the schemes that I'm talking about. So this is a solar photovoltaic available in MATLAB, with the battery available in MATLAB. Then there's a load, you can use resistive load or RL load or whatever AC load. Then I've used a boost converter. So this is how your typical boost converter looks like, right? Then you talk about that bidirectional converter I was discussing. Bidirectional converter. Inverter, you take just simple edge bridge. Then there is a LC filter. So all these things I'm talking in terms of this theory. This you can study from this MATLAB simulation also, and I'll down the line I'll show you some hardware results also. So all these things are pretty much tested, and we also published few papers. So if you are interested, you can go through them for more details. Yeah, okay, I'd like to resume because there are so many things. I'll try to wind up. And then, am I audible?
Sir, yes, sir, it's audible.
Yeah. Sorry, I could not extend the break longer because on the other side, I have some other commitments.
For your side only, because participants, whatever the time they need, they took break.
Yeah, they can. Yeah. So let me quickly go through it, and then next up, I'll be discussing little bit about this basic control philosophy, and then I'll tell you how you can tackle this problem. And while designing a new converter, what one philosophy that we follow, which can help you in designing your own converter. So that I'll address. So this control philosophy, I believe you must have understood. Just taking up this capacitor voltage as a clue, we can take a decision of mode change, right? So generally, I just give you brief summary what we do. So let's say you're doing MPPT. By this DC-DC converter, you are doing MPPT. By this DC to AC converter, you are controlling the load voltage. And by bidirectional converter, you are controlling the battery. Now, let's say the situation was pretty good. My solar power was 400 watt. Load demand was 200 watt. And that extra 200 watt, we are charging the battery. Right, and this is MPPT mode. Everything is healthy, no problem. It is MPPT mode. Now let's say since battery is charging, after some time battery got fully charged. Right. So what will happen? This battery converter will stop taking charge, right? Because it's already saw battery is fully charged, so it will stop taking power from this side, right? So as if it got disconnected, it will turn off all its switching devices, and this MPPT control, it does not know what happened to battery because this is a separate converter. So it will keep on doing the MPPT, And as a result, this capacitor voltage will start increasing. Initially, it was actually controlled by this battery converter. But as this power is now extra, so this capacitor voltage will keep on increasing. So we set an upper limit, maybe let's say 90 volt. So as soon as we see that the capacitor voltage has become 90 volt, we understand that battery is fully charged. This converter will understand. So without directly talking to each of them, without direct communication, it will get an indication that there is some problem with the battery. Maybe battery is fully charged. That's why this capacitor voltage is built up to high voltage. So then it will get out of MPPT. Right. So what it will now next start doing is that it will do control such that this power now becomes 200 watt instead of 400 watt. So how it can do that? So what it will do, it will keep on measuring this voltage, right? And it will start reducing its power. So from 400, it will start decreasing the power, and it will continue till a balance is reached where it gives 200 watt. So how it does that? Simply, if you remember the power versus voltage curve, initially it was there and power was this. So this is PV, this is IV, right? So initially it was there, maybe some let's say 36 volt and 400 watt. So if you can shift this side, you know, maybe 40 volt or so, you'll see your power is coming down, maybe 200 watt. Okay, so how it does that? Simply what it will do, it will start controlling the output voltage. Initially, it was controlling the input voltage. Now it will start controlling the output voltage. Right. So once it sees the output voltage is 90 volt, whereas reference voltage is 72 volt, which is my desired voltage. So you know there is an error. So it will change its duty ratio. If it sees that error is further increasing, it will change duty ratio in a reverse direction, right? So then error comes down. So when it changes a duty ratio in suitable direction, you know, if you are deviating from MPPT and maybe you are ending up with some other point. So this is how from MPPT you can shift to non-MPPT without putting some communication between all these converters. You can decide based on just seeing this capacitor voltage. Similarly, let's say you are doing it fine. You are doing it MPPT, non-MPPT. So solar power is 200, load demand is 200. And battery was fully charged, so it kind of become ideal. So now let's say load demand has increased to 400 watt. So solar, let's say it has increased to 500 watt. So solar will start to take up this load demand. So from 200, it will go to 300, it will go to 400, which is its maximum, right? So after that, it cannot cater the load demand. So this extra power will start coming from the capacitor voltage, and this capacitor stored energy, and capacitor voltage will now start falling. So as soon as it falls below, let's say 50 volt or something, that a lower margin, you know there is a power balance problem, that solar power is less than what is required by the load. So you now start discharging the battery. So all this philosophy you can control by just putting a limit on this DC-link voltage. So by sensing the DC-link voltage, you know whether there is a power balance, whether it is solar power is more, solar power is less. All those decisions you can take. So I'm not going into every detail. All these things are mentioned in our papers, so you can go through it. So all these discussions I've made, I'm not going to much detail because there is some other point to discuss. So how we all do this with respect to example, I've written very clearly. So just you have to sit down in peace of mind and you can understand all this concept. So next up, yeah. So how do I take all these decisions in terms of nice control philosophy? Everything is mentioned. So I'll be sharing you the slides. You can go through it. For more details, you can go through our paper. So this is one of the interesting paper we worked on. Instead of putting a low frequency transformer, we designed a new inverter. So basically what we did, one buck boost DC-DC converter and one full bridge inverter we have integrated together, and we came up with a new inverter. So So this can be a boost type inverter. So in earlier case you saw is what inverter we studied generally is a buck type of inverter. So to get 230 volt RMS, your input voltage required was 360 to 400. This is a buck type of inverter, right? So with that buck type of inverter, we have integrated the buck boost structure. That is how we got a new inverter, and that was done. But the main approach that I'm going to tell you is even the next approach. So whatever we have studied till now, based on this structure, right? If you don't want to have a low frequency transformer, you have one more DC-DC converter here to give you the required gain, maybe a flyback, or maybe a forward, or maybe a full bridge, depending on your requirement. Okay. Yeah. So from this point onward, please pay attention because some interesting features are going to come up. So what is the problem with this architecture? One problem you can see when charging the battery, there is two converter coming in the cascade path. So that means your battery charging efficiency will be less, right? This is one of the problem. Another problem is that, you know, solar power is not available for more than half of a day. During night time, solar power is not available. During daytime also, it is not entirely available. So that means the utilization of this converter, which are dedicated for solar photovoltaic, this utilization is very poor, right? So you are keeping a dedicated converter for solar photovoltaic, which is not working for more than half of day. So its utilization is maybe less than 30 or 40%. So you are paying extra money, but that guy is doing work for maybe some part of the time. So how can you address this two main problem? One problem is this utilization. Another problem is in the battery charging part, you have two converters, right? So to solve this, we came up with a new approach. So we wanted to eliminate this dedicated converter. That was the one of the main approach. So if I can eliminate this, all this problem can be solved. So then we came up with this approach. So I'll tell you how this. Before that, if you talk about this kind of architecture, right? So this solar converter, if you use a boost converter, it need one switch. Bidirectional converter need two switches, and this need 4 switches. If you look at this architecture, it needs more than 7 switches. This is 7. 4 plus 2 plus 1, 7. So the way we designed, we need only 6 switches. So how did we achieve all these things? Let me quickly tell you, without using low frequency transformer. So the starting point was, we understood that if I want to solar and battery voltage, their voltage levels will be using less. So for example, we are using 36 volt, by my load request to 30 volt. So one of the main requirement was that we have to increase the voltage boosting. So when voltage boosting comes to your mind, you think of connecting your equipments in series, right? So first point we started that let's connect battery and solar photovoltaic in series. So that will give me the voltage boosting without using any converter, right? That is the starting point. But the problem is, philosophy wise, you know, battery and PV has to carry same amount of current because they are connected in series. So that is a drawback, right? Because solar photovoltaic current could be anything, and battery current could be anything, right? Depends on their battery voltage. Solar current will depend on time of day, environment condition. It will change. So the same current I should not allow through battery because battery need to charge, needs to discharge. So we need another control element here, right? So to take care of balance between required photovoltaic current and battery current, you need a third terminal which can take care of the differences so that you can control them at their desired values. So this third terminal is introduced. Now in this terminal you can connect an R, you can connect an L, you can connect a C, right? R we don't want because it is lossy. L we have connected. C why we don't want? Because you know capacitor, controlling capacitor current is generally we don't do. We do capacitor voltage control, right? But here we need an element which needs for current control because we need to control the battery and PV current. We need to ensure they are different. And so this control inductor was the most suitable element. So we connected an inductor there. Okay. So now this gives an interesting feature that if I connect and switch here, right? So when I turn on the switch, I can have this current flowing from PV to inductor, and when the switch is off, this inductor current will circulate like this. So it simply indicates I can have battery charger from this. And in between PV and battery, you see only one converter is there. So you have eliminated that extra converter requirement. So this is the starting point. Next is we have to understand what happens when solar is not there, during night time. So this is the regular path. So when solar is not there, so this is not there, I have a capacitor. So if I want to maintain this voltage, what I can do, I can turn on this switch, so current will flow like this. When switch is off, current will flow like this, right? So I can connect my load maybe here. So what will happen, the load will see battery voltage plus PV voltage, right? So there's already inherent boosting in the system. And if you look from battery to load, it is kind of a boost converter. If you see battery to solar, it is a buck boost converter. Remember buck boost converter. Plus minus. So when this switch is turned on, inductor current just connects in parallel to the source, which is same as this, right? When switch is turned on, inductor just comes in parallel to the solar photovoltaic. When switch is off, the stored energy of inductor gets to the load, right? So we have made this converter bidirectional now. So either you can have power from battery to solar or solar to battery. So it's just basically buck boost converter connected in a different fashion. Of course, this is not our contribution. This was already used in literature in several other configurations, but we put it, we used it in our application nicely. So we made these switches bidirectional, so you can have power flow from battery to PV, PV to battery. You can connect a load here, right? Okay. So this gives you a very nice control features. Battery voltage is generally steep voltage. So by controlling this duty ratio, you can control this voltage amplitude, right? And if you can control this voltage at VMPP, this VMPP will come from your MPPT algorithm, right? So if you can control this voltage as VMPP, your MPPT is done. That is a very nice feature. And you can control this inductor current and to protect the battery from overcharge or discharge. All those things can be done. That is again a very nice control challenge. So next up, what we observed is this point. If I just extend this point here, A and O, the voltage at VAO looks like this. So when this S1 is on, this voltage is high. When S1 is off, S2 is on, so this voltage is 0. So this will remind you a converter which you have studied is a buck converter. Right? So what is this voltage? If I point it A and O, so when switch is on, this VAO is same as VDC. When switch is off, this voltage is 0. So this point is similar to a buck converter voltage that you get. So you can, this two you can club together. Right? So this is like a buck converter. So now you join them together, what you are getting? This nice converter, right? So you have a load here. If you don't want to connect your load directly parallel, you can connect your load here, right? So basically, what is this concept? It's concept of integrating different converters, separate converters to form an integrated solution, so that you can design a converter which can serve the purpose of two or more converter. So you can see this is a very nice example of how you can come up with your own integrated converter. Of course, the picture is not over yet. So I hope till this part is clear. If you forget about this L and L part, this part is like a buck converter. If you forget about this part, yeah, someone mic is.
Sorry, I mute it. It's only turn on, I think. Sir, Dibender, sir. Sir, your voice is not audible. Hello, sir. Dibender, sir, your voice is not audible. Just
unmute, sir. Unmute. Dibender, sir, unmute your. Hello.
Sir, Dibankar, sir, unmute your audio. Dibankar, sir. Okay. Sir, Dibankar, sir. Hello. Dibankar, sir. Hello, Dibankar, sir. Yes, I think connectivity problems are disconnected. Dear participant, this resource person joined within 1 or 2 minutes. I think due to network.
Yes, sir came, sir.
Yeah. Am I audible?
Yes, yes, sir.
Okay. I don't know what is the problem, but yeah, let me again start.
Yes, sir.
Yes.
Please let me know whether the slides are visible.
Yes, yes, sir.
Okay. Okay. Yeah. Sorry for the interruption. Yeah. So what I was telling you is that basically you can play with this basic converter and you can come up with your own integrated converter. So the way we did, you can see it's a buck boost converter and a buck converter. We club them together and we come up with a nice integrated converter. And another interesting point you can observe, the voltage waveform in this inductor, as you know, when switch is turned on, it is positive. When switch is turned off, it is negative. Like a buck converter, typical buck converter, this waveform looks like voltage across inductor has to be, average value has to be 0. So sometimes it is positive, sometimes it is negative, right? So that indicates you can put a high frequency transformer into it. So then taking clue from that, we have connected a high frequency transformer instead of inductor, right? And secondary side of the transformer, we have used a voltage doubler rectifier to give us more voltage boosting. Is a voltage doubler rectifier. So instead of using full bridge rectifier, those two diodes in full bridge rectifier are replaced by capacitor. So this is a voltage doubler circuit, again a standard circuit. So we came up with this as you can see. So basically this secondary side of the transformer will be connecting an inverter and then load. So it represents the load part of your transformer. So this is how this entire scheme was developed. So what you can see, you can do maximum power point tracking. You can do high voltage boosting because you have a transformer embedded into the scheme. And by controlling this inductor current, we'll be putting it in an inner current control loop. And by putting a limit properly, you can control battery overcharge, battery over discharge, all those. So in a single converter, we achieved all whatever we wanted. The MPPT you can do, battery charge control you can do, voltage boosting you can do. You have isolation also. Sometimes isolation is required for leakage current issues, right? So several, and then we eliminated dedicated converter for solar. Battery charging efficiency is improved. So all those things we could achieve using this scheme. And this is how the complete scheme looks like. So at the output of this DC-DC converter, you have a simple edge bridge inverter. If you want to reduce the switch count, you can make is a hub bridge inverter also, right? Because already midpoint is available to you. So you can use simple hub bridge converter also. So see, by using only 4 switches, you can design an entire standalone scheme. So this was our contribution and it was published in IEEE Transition on Industrial Electronics. So you can get more details. So how do you control the entire scheme? is given over there. If time permits, you go. Basic principle is same, right? You have to see this capacitor voltage and put proper limit on the inductor current control, so you can control battery voltage, battery overcharge, battery discharge. So we developed this hardware and it was tested for 500 VA and it was doing nice. So in efficiency, everything, it was coming pretty perfect. But one of the problem we had in this scheme was that see the battery current and PV current, if you don't use additional filter, so if you're not using any additional filter, you can see this battery current is not continuous. PV current is also not continuous because this current is discontinuous. Switch on and off. But battery current, if it is continuous, it is better for it lifetime. So we had to use additional filter for battery and a large capacitor for the PV because this current was discontinuous. So to solve these issues, we came up with another scheme where the battery and PV, the main structure of the scheme is more or less same, as you can see, but this battery and PV are now connected through a dedicated inductor. So that common inductor was eliminated. It was split into two, and battery is connected through inductor port, and PV is also connected through inductor port. So this capacitor size can be reduced, right? So the capacitor size, if you can reduce, you can use polypropylene capacitor or some ceramic capacitor, which is having better reliability as compared to your electrolytic capacitor. Of course, this scheme also has some drawbacks which you can target, and you can, as I mentioned, there are several challenges still here. One of the challenges I'll tell you very straightforwardly, the ripple current of this capacitor, if you see, they are not very less. So you have to connect actually few capacitor in parallel, right? And still we have not completed the analysis of ZCS, ZBS, all those things we have not optimized. So that can itself be another work. And this control philosophy, we have not developed it fully. So there is still open challenges. So some of my students are working on it. You can also join our team, or you can also start working on this kind of problems. So as you can see, from taking clue from last scheme, we have derived this scheme. Similarly, taking clue from this scheme, you can start deriving your own other schemes also. So one of my students is working on that also. So as I told in the beginning, that if you understand these schemes properly, you can have your own direction for the research, right? This area, standalone scheme, you won't find many papers, because this off-grid system requirement is mostly for the countries which are developing countries or underdeveloped countries. Most of the developed countries, they already have grid connection everywhere. So they don't work on this area much, right? So as a result, a number of paper published in this area is not very high. So there is a high chance that you can also come up with your very good idea and you can publish decent papers. Yeah. So with this, I posted some question for you. Maybe at the end you can see. And let me quickly go through another interesting scheme. So some of people ask me, what is the cost comparison of if I take DC load versus AC load? What is the cost of panel, all those things. So for this, you can follow some lectures by Professor Chetan Singh Solanki, IIT Bombay. So I've taken this number from his lectures. So if you want to design a system, what are the main cost, and per watt, what are the figures, right? So the solar panel, inverter, battery charge controller, those things has to be rated for watt, and your battery has to be rated for watt into hour, right? So that's why the battery cost will be more than half of the total cost. And if you, for example, another comparison, you can see this charge controller, which is basically a DC to DC converter. Its cost is much lesser than the inverter cost, right? Inverters are generally costlier. So if you can eliminate that AC load, you can use DC load, your converter cost comes down. Okay, and DC loads are generally most having better efficiency. And if you can select proper voltage level, you can eliminate one converter stages altogether. So that is how DC load gives several benefits. But of course, DC loads are not popular yet, so you don't get commercially available load much. But maybe in the near future, they will come. So we came up with another interesting concept of how can we design 3-port converter. So as I mentioned, if you want to design a Again, this is a very nice concept. Please pay attention. Maybe and I'll be winding up in next 5 minutes. So try to pay attention. So if you want to design a DC standalone scheme, one is that you connect a solar photovoltaic, then a DC-DC converter. Then you may connect your load here. Then from here you have another bidirectional converter, right? Then you connect your battery. That could be one of the solution. Another could be you connect a battery, then DC DC, then there is a battery, then another DC DC, there is a load, DC load. So in both the cases, you see you need two separate converters. But can we design an integrated system so that we can club these converters together and come up with a concept called 3-port converter, which requires less number of switches as compared to this dedicated approach. And we expect that its efficiency will also be improved. So how can you design an integrated system for DC load, right? So we come up with a family of converter. We proposed a synthesis method by which you can design this kind of integrated converter from any standard converter. So we'll take example of a boost converter and I'll tell you how you can design this system. So to start with, what we take, you need solar, you need battery, and we want battery current to be continuous. So we have this batteries energy storage element cell. So what is there? You have a battery, you have an inductor, you have a switch, right? So this is your battery control port you can think of. Now you take any standard DC-DC converter, like this is a boost converter. Okay, and what you do, you find out what is the active switch in that standard converter. By active switch, we mean, generally we control that switch to control the converter. For boost converter, what you do, you turn on and turn off this switch to control the boost converter. So this is the active switch for us. Similarly, for buck converter, buck boost converter, you know which switch is active switch. And that switch, there is a standardly a diode is used in this conventional converter. So we are replacing that diode by a MOSFET, maybe MOSFET or IGBT. That is the change. So you take any conventional converter, DC-DC converter, replace the diode by a switch, right? Without changing the diode direction, right? Diode direction you keep same and use a switch on it and identify the main active switch. In series of that main active switch, you take out a cutout portion and you insert this cell. That is how your job is done. So this is the resultant scheme. So this was the active switch. In series to this point is actually this point only. Right? You can neglect. This is all same potential point. So you take this energy storage element cell and connect in series with this active switch, and that's how you get a new 3-port converter. Right? So you can see, as compared to all those dedicated converter approach, you will be requiring one switch less, one switch or one diode less, right? And you can design your solar and battery both to be continuous current port, you can see. So which is very beneficial most of the time. So how do I extend this idea? And you can get the gain expression. You'll see they're completely decoupled. So you can control PV voltage, you can control load voltage, everything you can do. So how can you apply this concept to some advanced converter? For example, 2-inductor boost converter. It's a boost converter, modified boost converter. So again, you identify the active switch, you put that energy storage cell. So you integrate your battery with this. If you take Z source kind of inverter, right? Advanced. Again, you identify the main switch, insert this energy storage cell. A new converter is done. Quadratic boost converter, which is a very popular converter for high gain application. Again, you figure out what is the active switch. Yeah, connect a energy storage cell. So your 3-port converter standalone scheme is done. So we also proposed a standard control technique which is useful for all these schemes. It's not just for one scheme, a generalized scheme. And also we verified all this concept through hardware in all lab, and we saw this working pretty fine.
Yeah, so with this, let me conclude. Some part which I'm not going to discuss is what is this leakage current and what is their impact. What is this residual current, which is very, very important for your home appliances. You know, if you get shock, who is protecting you? How do you do home wiring, etc. Right? Where is this residual circuit breaker? So all these are very important point, but I think due to shortage of time, I'm not going to discuss. I'll be sharing you the slides. This is very important part. What amount of current your body can withstand and what will be impact on your body, all those things. These are again some interesting points, so I'm not going to spend time. It's almost 12. So if you want to get connected to me, of course I'll be open to questions in a minute. But still I believe some question might be there in your mind which I won't be addressing due to shortage of time. So you can write a mail to me. And I've recently started my YouTube channel. Some lectures are already uploaded there. So you can also search by this name. And I'll be putting some more lectures in this December. That is our semester break time. And if you want to see my recent publication, you can follow this Google Scholar. And also, if you have an active LinkedIn profile, please send me a connection request. Right? So we can work in near future. Maybe we can collaborate. So the way you can collaborate with us, which we actively looking for. So for example, if you have some idea, but you don't have student to work on, you have idea, but you don't have student, you don't have hardware facility, right? So in our lab, we do have some student working on every time. We have hardware facility, so we can collaborate. Sometimes you don't have idea what to do, right? But you have student. You have you have manpower to work on, but you don't know what exactly to be done for publishing a paper or some good work. So we can help you with that. Maybe we can share some of our idea, and you know, it's a collaborative impact, right? So in both the way we can, if you are interested, you know, it's nowadays everything is collaborative research, right? So we can form a team, and hopefully, yeah, someday you also visit IIT Kharagpur, right? And we can show you our labs, etc. And hopefully you'll enjoy this. So with this, let me conclude this part. If you have any question, I'll be happy to answer, maybe for next 5-10 minutes.
Sir, good morning, sir. This is Ravi Kumar. Sir, I have one question.
Hi, Ravi. Yes, please.
Sir, my question is, if I'm going to use a multi-port converter in case of DC microgrid where I have, let us say, one battery and one supercapacitor. So there, what kind of control generally we look for, sir? Like if I take one multi-port isolated converter structure, what you have shown, what kind of control strategy generally is being adopted to address the load, let us say pulsed load. We have pulsed load where we need to feed the load from solar and battery as per the need. So where we have a bidirectional DC-DC converter also, so that we have a bidirectional power flow. So and also maybe possible, if possible, the ZVS feature if you want to include. What kind of control strategy generally is being adopted? Because what I understood is we need multi-port isolated. Generally, I see about phase shift control or phase shift plus duty cycle control. So is there any other new strategy or some popular strategy being adopted to achieve this bidirectional power flow and if possible some ZVS switching?
Yeah, so what I understood your question is basically you have an isolated converter for integrating your battery energy storage to maybe microgrid, right?
Exactly, sir. Yes, sir.
Yeah, and how do you control that?
Yes, sir. Is there any control strategy which is which can be adopted? Because I'm doing this area of that multi-port isolated converter. So I want to know what are the control strategies which can be researched in that area.
Yeah. So as you rightly pointed out, see this basically you're talking about a dual active bridge, right?
Yes, sir.
Yeah. So for that there are several control philosophy, and one of the most popular, as you said, is phase angle control, basically, with some ZVS control. So there are several schemes available, and it is still a research work. It is not like saturated. So how to control dual active bridge is still a research challenge.
Okay, sir.
So this phase angle control is widely used. And it has various different methodology to implement that philosophy. Phase angle advance, or whether you are controlling delay, how much you are controlling. So in fact, there are several studies. I don't remember the exact name, but this is still research work, and a lot of things are going on. Maybe I can suggest you some paper on this.
Yes, sir.
Offline, right?
Yes, sir.
Yeah. This is still an interesting area to work on. It's not saturated.
Okay, sir. Thank you, sir. Sir, your contact mail, can you put in the WhatsApp group, sir? I'm not able to see that slide where you kept your detail. Can you please box
let me
mail ID if possible?
Yeah, it is. In fact, if you search by my name, right, you will mail Dipankar Debnath, IIT Kharagpur. If you search by my name, you will get my profile easily, and there everything is mentioned.
Sir, sorry for the disturbance. Sir,
Yeah.
already this is Dipankar sir. It's having full biodata available in our this WhatsApp group. You find this one. It's having mail ID. Everything is there. Even those are publications and research interests. Everything is available in these informations. Because every day we provided for the resource person profile to the participants. This is for your kind information.
Yeah, maybe he did not get time to.
Yeah, I didn't look out. Sorry for that. Surely, sir.
Yeah. Any other questions?
Thank you, Dipankar sir. It's having very nice and excellent. It's a presentation. It's discussed a lot of practical information, and it's a session also. It's more interactive. During the starting time, the participants sent this around 25 plus. It's a present condition. It's having 75 plus. Based on your interest, many of the participants are joined. It's continuously watching your lecture also. Thank you. It's having once again, Mr. Sainath. Please give the vote of thanks to our resource persons, followed by our HOD, Dr. Raid, given for the concluding remarks for this Sttp. Sainath, sir.
Yes, sir. Yes, sir.
Please give the vote of thanks. It's followed by HOD, sir, given for the concluding remarks.
With your permission, sir. Very good afternoon, sir. It's a very, very great lecture, sir. Very real time and very useful, sir. These topics has really created a research culture among us, and also these topics has triggered the many research problems. This is very useful, and I'm very, very thankful for you, sir, for spending your valuable time and giving this lecture. And we are also waiting for your future webinars also. And thank you, sir. Thank you once again on behalf of EEE Department Bvrit. We are thankful for you, sir.
Thank you. Thank you for giving me the opportunity. It's always a pleasure to interact with several participants. And I think, thank you for giving me this opportunity, rather.
Sir, welcome, sir.
Yeah.
Sir, our HOD given for this concluding remarks. Mr. Dr. Raidu, sir, please give your valuable concluding remark for our participants.
Yeah, thank you, Dr. Saravanan, sir. Thank you very much. I would like to thank, starting from the chairman of this Sri Vishnu Educational Society, Sri KV Vishnu Raju, sir, and the vice chairman, Sri Ravichandran Rajagopal, sir, and secretary Aditya Visam, sir, and our beloved principal, Dr. K. Lakshmi Prasad, sir, and all my program coordinator, Dr. Saravanan, and organizing coordinators, Chandrababu, Naresh Kumar, Ravinder, and all my people of the department who supported a lot from last 1 week. Continuously, they striving hard to make it a grand success. And special thanks to Sainath, Janice, and Srinivasu, and Ramchandar, Mahesh, sir, Santosh, and Rama madam, and all my organizing committee like Gopal, Vijayabhaskar Reddy, Pramila madam, and Subram Reddy, Ramkrishna Garu, and Bangar Raju, Muniswar, Anjit Kumar, Vijay Kumar, and Girish Kumar, Murali, our Prasad, Dhanunjay, Vijay Kumar, and Harish Kumar for their continuous support, even in this pandemic situation, for making this event, this FDP a grand success. And I am thanking all my speakers, starting from the chief guest Dr. Dheeraj Khatot, sir, and Dr. Ramesh Bansal, sir, and Pramalata madam, Chittubabu, sir, and Dr. Ravi Kumar Garu, Dr. Ravi Teja, Dr. Chandrasekhar, sir, and Hari Krishna, sir, and Dr. N.K. Swami Naidu, Dr. Hiralal, and Dr. Devankar, And finally, I am thanking you. Thank you very much. And we are conducting from December 7th also one more FDP on electric vehicle technology components and challenges from the December 7th onwards. I am thank you very much, Dipankar sir, for your continuous and last 1 hour lecture. I am also listening. Unfortunately, with other activities we were involved. That's why I have not taken other sessions, but I involved in your session and I am taking your session, sir, from the morning itself. I am special thank to Dipankar sir. We look forward your cooperation for the benefit of this community on behalf of the Tribal Department of B.V. Raju Institute of Technology, Narsapur. I thank a lot, and special thanks to my coordinator, Dr. Saravanan, for making this FDP a grand success. And finally, the participants who come from different colleges and their managements also, I'm thanking for giving the time to attend all these FDPs conducted from last 4 months. Every month we are conducting. So thank you very much. Thank you, Saravanan sir. Thank you very much.
Thank you, sir. Thank you, Raid sir. Thank you, Dibankar sir. It's give a wonderful lecture. Once again, I thank you on behalf of our Bvrit. Thank you, sir. Dear participants, you next session is the feedback session. Please unmute your audio and give your valuable feedback to us to improve in future in what way we are conducted the next program. Also, it's very helpful for us. For your expect your cooperation support in this regard. So please unmute your audio and give your valuable feedback to me.
Yeah, so Dr. Saravanan, can I take a leave? I mean,
yes, sir.
If it's okay.
It's going. Okay. Thank you, sir. Thank you, Gandhi. Yeah. Sir. Thank you, sir, very much, sir.
Yeah. Thank you all the participants for bearing me for 2 hours. Thank you. Thank you very much. Bye.